Hello students, this is our tutorial hub. I've already launched a video on linear programming problem, and there I discussed some linear programming problems. So I continue this, and I wish to discuss more videos about linear programming problem with different cases. So let's start. Now we consider a case of the minimization problem. The problem is given in this way: minimize z, the objective function which we have to minimize. This is given x1 plus x2. Uh, in the first video, I have said that in graphical method, just we can take two variables, because in graphical method we have two axes in Cartesian plan, so we cannot exceed more variables, just can take two variables. Now this is subject to the constants are 5x1 plus 9x2 less than equal to 45. So there is a problem because it is a problem of a minimization problem, and the constant is given less than equal to. So we at sudden transfer it in a greater than equal to form. So it is not necessary in graphical method, but for clearly understand, we need to transfer it in the greater than or equal to constant. So we'll take negative on the both sides. I am again saying that it does not matter for graphical methods, but for clear understand, so that we can clearly understand, we will take the constant for minimization problem greater than equal to minus 45, and we pen through the uh, earlier constant. Now this is already transformed into greater than equal to constant. Now one more constant is given, x1 plus x2 greater than equal to 2, and one more constant is given, x2 less than equal to 4. So I have already said it does not matter less than equal to. We can transform it also, and I am showing pen. It is transferred in this way: minus x2 greater than equal to minus 4, and again pen through this constant. Now x1 and x2 greater than equal to g. They are non-negative. We have to, using these constants, we have to minimize the objective function. So let's use the graphical method. Let's draw the picture. So I have already done the picture, and now drawing this. Use this. This is there are two axes. This is x-axis. This is y-axis. This is the origin. This is a special case. So there are the marks on the axis. 5, 10, so on. Now here 10, so on. So the equation, first constraint we will treat as a equation, that was 5x1 9x2 equal to 45. It will pass through the point uh, 0 5, this point, and this point 90 90. So the straight line will be in this way. This is the equation. Transform the constant as a equation, and we will get the equation in this way: 5x1 plus 9x2 equal to 45. So which area indicates it? If we put here, and there was the constant less than equal to actually given. I have transformed it is greater than equal to, but it is given less than equal to. So it does not matter. So if I put 0 0, then 0 0 comes, 0 is less than equal to 45, less than 45. So the 0 origin comes under the region. So this is the region solution area of the constant 5x1 plus 9x2 less than or equal to 45. Now another constraint is pass through point 2 2 and 2. It will be drawn in this way, in this way. So it is x1 plus x2 is equal to 2. Here also the constant taken as equation. So here also given the constant greater than equal to. Now if I put the origin 0 0, then 0 is not greater than 2. So origin does not the area which contains the origin does not be the solution space of the constant. So uh, the other side which does not contains the origin will be the solution space. So this area will be the solution space. Now we are given x2 is equal to 4 also. So another constant x2 is equal to 4 will be here. Here will be another equation x2 is equal to 4. So x2 is equal to 4. There the constant given less than equal to. If we will take 0 0 point origin, just 0 putting, then 0 is less than 4. So the region will be in this solution space contains the origin. So and the non-negative conditions of of x1 and x2 will give the solution space in the first quadrant. The solution is the first quadrant. So combining all the constants common region, will get this area. I'm now marking it H A B C D E and A. So A B C D E E E A will be the feasible solution space. It is the feasible solution space because this region satisfies all the constants conditions. This is the feasible solution space. Solution space. So we have to find out the optimal solution for the objective function. So here, if we, I have told you that one way is that to put corner points in the objective function and to find out the uh, the objective function, objective minimize objective value, minimized value of the objective function. So this is a one way. Another way to draw the price line, and where it this is a problem, minimized problem, so it must comes to the origin. So I am first drawing the uh, price straight line. Now putting I am this 0 4, and the uh, problem was given as z equal to x1 plus x2. So one corner point I am putting here x1 plus x2. If we put 0 4, then z equal to z will be z equal to 4. So here we will get the price straight line. Here we will get a price straight line. Now it also passed through 4 0 point. This will be the z equal to 4 price straight line. And the funniest thing is that the z equal to 4, the price straight line, when because it is a minimization problem, it always comes towards the origin. So when it comes towards the origin, it will not coincide with a point but a straight line x1 plus x2 is equal to 2. So since there are infinite points in the straight line x1 plus x2 is equal to 2, so there will be infinite solutions of the linear problem of this LPP, infinite solution. So any point on the straight line will give us the optimal solution, infinite solution. Infinite solutions. All the points on this straight line coincide with the price line when it comes towards the origin. So any point if we put 2 0 or 0 2 will give us the minimized. Minimized z is optimal solution of z. Optimal solution is z equal to 2 is the minimized minimum value of z. No point give this minimum value. 0 2 or 2 0 or any point on the straight line give us the minimum. It is a very important case because here we get infinite number of optimal solutions. Infinite number of optimal solutions. So this is very important case. Remember this. And this is one way. Another way you can easily put the corner points. One corner point 2 0 0 2. Other is 9 0. There is 5 0 5. If we will put, then you will get that 2 0 and 0 2 will give the minimum values, but it does not clearly show that the number of solutions. You will get two optimal solutions, but here this is a special case. Here actually no two corner points give the same result, but no two we will not get two optimal solutions, but infinite number of solutions. Each point on the straight line gives optimal solution. So infinite number of solutions is a very special case. Now let's see another topic for unbounded cases. a case of maximization. Maximize z is equal to 3x1 plus 4x2 subject to x1 minus x2. They are given greater than equal to 0. I am not transforming it into less than because it is a problem of maximization. So the constant should be negative less than equal to. But I am not transforming. It does not matter. That's why. And the other is minus x1 plus 3x2 less than equal to 3. X1 and x2 are greater than equal to 0. Now we use the graphical method here again and draw the graph. So again I have already said, I have already done. I am just drawing the graph. I am not solving it. Just I will put the constant as a equation and draw the picture. So again I draw the axes. This is the origin. Five. This is 10. This is 5. Minus 1, minus 2, minus 3, minus 4. This is minus 3. Now when we draw the first constraint, then we will get it will pass through minus 3 0, minus 3 0 and 1 and 0 1. So the straight line will be so this is the equation. Minus x1 plus 3x2 is equal to 3. Now another straight line will pass through the origin, so there will be a point and it will be uh, a straight line which tendency is 45 degree. So this will be just in this way. X1 minus x2 is equal to 0. X1 is equal to 0. One thing is, you please remember that x2 are the points of y-axis and x1 are the points in x-axis. I am not writing xy but x1 x2. So here if we put the constants are given, they are given greater than equal to, we will find out the solution space, and here the given the constant is less than equal to, so we will find out the solution space. If we put the origin 0 0, then it will get that 0 is less than 3, then the area is the solution space for this constraint. This area is the solution space of this constraint. And if we put here 0 0, then 0 is equal to 0. And if we put another point 0 0 0 0 cannot decide, we will put a point like 1 0. this point to test where it lies of this straight line in this right side or left side. So 1 0 means 1 greater than 0. Yes, this side is the solution for this straight line. Now, and the first quadrant also, this since this one x2 non-negative, so this region is a common region or feasible solution space for this problem. So this is unbounded. There are lots of points, a infinite number of points in this space. It is unbounded. There is unbounded solutions. The feasible solution is unbounded. So here if we put point A, so how we maximize the objective function here? Here we are not getting the corner points, so we first draw the price straight line. Here price straight line will be the objective function was given z equal to 3x1 plus 4x2. So here you can look that, and this point is, this is the point. Its coordinate will be, we put here x2, then it will be 2x2, 3 by 2, 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 3 by 2. This is the point. So we will take a straight line which is passes through this point, and if we will take the value of it will be, it will be 3 by 2, 3 by 2. If we put, then we will get 9 by 2 plus 12 by 2, and this will be 21 by 2. Assist line will take here 0 3 first 0 3 will give us z equal to 12. We will not take this value. We will put 0 3 this point 0 3. So we will get z equal to 12 and 40 and 40 this point. This will give the price straight line. So it will be in this way. This is the price straight line. Straight. This will be the price straight line actually. This is actually z equal to 12. I have taken by putting here 0 3 and 405. This is the first price straight line z equal to 12. But when this is a problem of maximization, so it goes through from the origin. So there are unbounded, this is unbounded solution where it will get the corner point, it will not get the corner point. And how we will get the solution? So here we will not get any solution. It is a unbounded solution. It is a unbounded solution. Means the maximized value is unbounded. This problem does not have any optimal solution but an unbounded solution. So for cases of unboundedness, everywhere you will not get unboundedness. Some problems also have, though it is a unbounded problem, but it can have optimal solution. This is also another case, but here we will not getting the straight line as goes through. It does not coincide with any of the point. So for this unbounded solution, unbounded case, we are not getting any optimal solution. For but another case, I am showing you. Here we will get a optimal solution, though it is unbounded. Consider another case is maximization problem. Max z is equal to 2x1 2x1 minus x2 subject to x1 minus x2 less than equal to 1, x1 less than equal to 3, and x1 x2 non-negative. X1 and x2 non-negative. Then we will again use the graphical method because it is a case of two variables. There are two decision variables, so we can use graphical method. So here a special is that it is also a unbounded problem, and there also will get unbounded solution, feasible solution, but it have a optimal solution. This is the specialty of this case. Now I am drawing the two axes. Here x and y. There are 6 marks here. Six marks, and here this is 0 origin, -1, -2, -2. So one constant, if we put it as a equation, it will pass through -1 0 this point and 1 0 this point, and we have the straight line in this way. get the straight line. It will be x1 minus x2 is equal to 1. And also we have given x1 less than equal to 3. So x put is a equation, then we will get x1, it will pass through the 30 point and parallel to the y-axis. This is x equal to x1 is equal to 3. So now we will test now then the solution space of this constraint. So there is given less than equal to, given less than equal to, here is also given less than equal to. Test is very important to find out the solution space. So when we will put here 0 0 to the region and the origin, actually 0 less than 1. So origin lies in this solution space. So this will be the solution space. This will be the solution space. And when we put here 0 point origin 0, 0 is less than 3. So origin lies in this of the constraint solution space. So this will be the solution space. Now because non-negative conditions are for two variables x1 and x2, so first quadrant and the common feasible common solution, the solution space which is the feasible solution for this constraint is this area. So this is the area which is the common for both. This will be up to x-axis, not below, up to x-axis. So if we put name o a b, and there this is an unbounded solution. You can look this, there is not any polygon which covers the solution space. Here on the up of this line they are unbounded, so any no polygon or straight line covers the solution. So the uh, feasible solution is unbounded, but actually what is the here we will get the optimal solution or not. This is the specialty of this case. This is unbounded solutions. Feasible solutions. Unbounded feasible solutions. So we will test that actually it has any optimal solution or not. It is a problem of maximization. So we will get the price straight line first. So how we will get price straight line? We will put z where z actually given z equal to 2x1 minus x2. So if we put here 1 0, the point 1 0, so we'll get 1. So we'll put here the point 1 0. So in this way we'll get 1 0 point. So 1 0, and here we get 0. If we put 1 0, then we will get z equal to 1. And if we again put z equal to 1, to getting the where the this line price system and the y-axis, we'll put here x1 equal to 0, then we'll get 1. So x2 will be, this is 0, this is 1 minus 1. So the price system will pass through in this way. Sorry, x2 if so minus 1 uh, and 0 if we will put, then we will get z equal to 1. So the price state passes through this point also, and if we put here half and 0, then we will get z equal to 1, half and 0. So actually there will be the point where the price state passes through. So in this way the price state line passes through, z equal to 1. This price state line for the maximization problem always keep away, go away from the origin. So when it go away, it actually meets at this corner point. This is the special case specialty. It is not going through and going away in the direction of the unbounded solutions, but it is going towards the a corner point. So we will get a optimal solution. This is the feasible solution is unbounded, but there exists an optimal solution. This point's coordinate is 3 2. This point's coordinate is 3 2. So the optimal value of the objective function will be, here we will get, it is 3 to the 6, 6 minus 2, 6 minus 2 equal to 4. So here we are getting the optimal solution. This is the result of this case. Here the feasible solution is unbounded, yet we have get the optimal solution. So keep watching these videos. Thanks for watching. Subscribe this channel, and share with your friends. Comment me if you like this video, and if you have any suggestion, then also of course comment me. Thanks. And in the next video, I continue with the inquiry problem and discuss our simplex method. So subscribe this channel. Thanks.